So I'm restating the proposition where we were on Tuesday. There are three main characters: a compact metric space. The application, the case we are interested in is projective space in RD. Then there's a map, a skew product defined on M cross P. The case we are interested in is when gx of V is the logarithm of ax of V divided by V. And then there's a space of functions that I call F. These are the functions for which this object is finite. You take, though they are defined on the product space, real functions, they are defined on the product space. You take the supremum over the second variable, and then you integrate with respect to the first variable. And this should be finite. This number here is called the norm. I think I denoted it as the one norm of phi. And again, the situation we are interested in is when, sorry, this is wrong. This is ax of v. So gx equals ax, a of x. And here, the case we are interested in is when, for in the projective space, is this function here. Okay, and our assumption that log plus a is integrable means precisely that this is finite. Okay, and the proposition says that the limits I of x equals, or s of x equals lim as n goes to infinity 1 over n of the supremum over v of of the sum from 0 to n minus 1 phi gj of xv, and the corresponding notion where instead of the supremum we take the infimum. So these two integrals exist, these two limits exist mu almost everywhere. Moreover, there exists G invariant probabilities eta I and eta S and eta I, such that, so these probabilities are on M cross P in this product space, such that the integral of S with respect to mu, with respect to mu, is equal to the integral of phi with respect to ds, to eta s, and the integral of I with respect to mu is equal to the integral of phi with respect to eta I. And this I think I forgot to write down. If you project eta s and eta I, the projection is mu. Okay, so the picture is you have the product space. This is M, this is P. Eta I and eta s are measures here. When you project them down, you get mu. When you project, this is the first projection, the first coordinates. Okay. So I'm going to prove this, and then the next step will be to consider this particular situation in linear cocycles to apply to that particular situation so that we are able to prove that in the statement of the Oscillides theorem we have a limit, not just a lim sup. Okay, so the proof is not very complicated. I'm going to for some reason. Okay, let Sn of x be this expression here. Sup over V of the sum So I claim that Sn, the sequence Sn, is subadditive. So let me first prove this claim. This is just a calculation. Sm plus n of x is the sup P of the sum okay. Now this sum here may be split into two parts, and I'm going to do that right away. I sum from 0 to n minus 1, and then I sum from 0 to n minus 1 phi gi of gm of xv. Right? Just breaking the sum into two parts, and this one is from 0 to m minus 1. This would start from m to m plus n minus 1, and I write it in this way. Okay. Now, the supremum of a sum is less or equal than the sum of the two supremums. Okay. And now if you look at the two terms, this is precisely Sm of x Maybe this one is a little bit trickier, so let me do it a little bit slower. Phi gi, and then I'm going to write this expression, which is fm of x, by definition, gm, and then some other vector, some expression I'm going to write like this. But anyway, what is important is that that the first coordinate here is fm. And now this second term, the second term, this one, is less or equal than the sup sum I from 0 to m minus 1 phi at gi fm of x w, where the sup is over all w's in P. Okay? You are taking the supremum over vectors here. When you change V, this also changes. But of course, if you take all the possible values that you can, all the possible elements that you can write here, you get a number that is at least as big. And then this now is, this is Sn of fm of x. Okay? So what I proved is that Sm plus n of x is less or equal than Sm of x plus Sn of fm of x. And that's precisely what I wanted to prove. That's what subadditivity means. Any question? When you say subadditive, I have to say with respect to some dynamical system, and the one that is relevant here is f. These are functions defined for points in M. Okay? So, as an immediate corollary from this claim, by the subadditive ergodic theorem, the limit S of x exists. And that's precisely what I'm claiming here. Exists mu almost everywhere. Okay? So the first claim that these limits exist is a special case of the subadditive ergodic theorem. I did the argument for S. The argument for I is just the same. The difference is that here, instead of less or equal, we get greater or equal than. This sequence IN, this sequence here, is super additive, but you just change the sign, put a minus sign, and it becomes subadditive. Okay, so we have this statement. Now we are going to consider sets like this. To get the rest of the proof, we are going to consider sets gamma n for each n, the set of points x, v in the product, where this supremum is attained. Where the supremum is attained. So such that the sum where the supremum is attained. So if you want to keep in mind the situation that we are interested in, I already explained last time that this, for the choices, the special choices here, means how much your matrix is expanding. This is the largest possible expansion. So these are the points where the largest possible expansion is attained. Okay? And I'm also going to denote gamma n of x to be the set of vectors of elements of P such that the pair xv belongs to gamma n. Now, I claim that gamma n x is compact and non-empty for every x in M. And the proof is very short. You look at the function sending v to this expression here. Okay, so it's a function from P to R. T is a real function. X is fixed. And this is a continuous function. I guess that is part of the definition. Yeah, I didn't say it. I should have said it. Such that this and phi x dot from P to R is continuous for every x in M. Okay, I'm not saying much about how phi depends on x or how g depends on x. This is just measurable. But in both cases, I want the functions to be continuous on the second variable. In our case, the case we are interested in, the second variable is the projective space, lives in the projective space, and we are dealing with matrices, and matrices are continuous, defined continuous functions in projective space. So everything is continuous in V, and so this is continuous, and P is compact. And every continuous function on a compact space attains its maximum, attains its supremum. So end of the proof. Now, there's another nice thing about gamma n. The set gamma n, this one, is measurable. Because all the functions that intervene here in the definition are measurable functions. Okay, I didn't write it, but it's measurable, measurable, and so gamma n is measurable. And there was a proposition last time on Tuesday saying that if the graph of a function is measurable, then the function itself is measurable. So this, by one of the, I think it was theorem B that I mentioned last time, implies that x goes to gamma n of x is measurable. Let me be a little bit more honest. It's not theorem B as I wrote it. I gave what I called theorem B is a corollary. It's exactly proposition 4.6 in the book. Last time I stated a more geometric consequence. Proposition 4.6 in the book gives exactly this. So this set depends measurably on the point, and the proposition also says, and there exists, and this is nice, there exists a measurable section, a measurable map from sigma, from M to P, there exists a measurable, that's part of the proposition. There exists a measurable map from M to P such that sigma of any point belongs to this set. That is, the set, the graph of sigma is contained in gamma n. Yeah. So what is the structure here? This is a map from M to. So where is the domain? The domain is the set of compact subsets of P. Okay. Now, what kind of structure does the set of compact subsets of a compact metric space have? Okay, we make a pause here. If P is compact metric space, then the set of compact subsets of P, this is abstract statement, is a metric space. What I mean by this is that there is a natural distance. So what is this distance? It's called the Hausdorff distance. Hausdorff distance. The distance between two compact sets is the smallest r such that K1 is contained in the ball of radius r around K2, and K2 is contained in the ball of radius r around K1. Okay, so two compact sets are close to each other if each one is contained in the neighborhood of the other, the small neighborhood of the other. Exercise, this is a distance. Hausdorff distance. We also talk of Hausdorff topology in this space. Hausdorff distance. Exercise, if P is a compact metric space, then this is also a compact metric space. It's nice. It's a compact metric space. Okay. So once I know that it is a metric space, it has a Borel sigma algebra, and measurability is with respect to that sigma algebra. The sigma algebra generated by the open sets of this metric space. So you see, measurability, this is something that I didn't have the chance to talk about at all last time. Measurability also has this interesting idea. a vector, for example, in the vector, the linear case, a vector bundle, a subbundle, is measurable. If it is measurable, then you can find some measurable vector fields. This would, in the linear case, this would be a vector field whose image is always contained in the subbundle. There is a measurable section to the subbundle. The reason I'm doing this is because I want to construct these invariant probability measures here. And the reason I want to do that is because then I will be able to use the ergodic theorem to go from lim sup to limits. Okay, keep in mind this fact. The assumptions imply that there exists some measurable vector space whose image such that sigma x is always a maximal expanding. So I'm going to fix the notation. Let's call this nu n. That's the notation in the book. Nu n, and here also nu n. Of course, it depends on n. Okay, so now I'm going to draw a picture here so that you keep in mind you have the space P for each x in M. Okay, and what we are saying is that it is possible to choose some element in P depending on x in such a way that these two conditions are satisfied. This point is measurable, depends measurably on x. This is the first condition. And the second condition is that nu n of x, so x nu n of x, belongs to this gamma n. Okay, you can choose one vector where the expansion is maximal, and you can do that in a measurable fashion. So now I'm going to I'm moving towards constructing these measures here, to constructing eta s. So what I do is I take Cn to be the measure, the probability in the product space given by Cn of a set is the measure of the set of points x such that xv is in E. So another picture, smaller picture. Such that sigma nu n of x nu n of x is in E. So you have some set E. And depending on your point x, it may happen that nu n of x is inside E or outside. Okay? You just measure, you take the measure of the set of points for which this is inside E. Okay? This measure is static. There's no invariance. There's no dynamical system. But now we construct eta n. We let eta n be 1 over n sum j from 0 to n minus 1 g j star of xi n. You just iterate it forward. And you take the limit of the iterates. Now I'm going to write a few properties. I'm not going to detail the arguments because they are written down. You have to check things, and it's not so interesting. They are written down. It's half a page. So I'm going to say what is important here. What are the properties? First property is that if you project Cn, you get mu. If you project Cn to the first variable, this is projection pi. If you project Cn, you get mu, and then as a consequence, if you project that average, you also get mu. It's one important property. The other important property is that there exists some subsequence going to infinity such that if you restrict to that subsequence, there's a limit. The sequence converges. Converges in weak star topology. Weak topology. There's not much that I can say about this. The space of probability measures can be given a topology, the weak star topology. And with this topology, the space of probability measures is compact. So any sequence is a metric, compact metric space. So any sequence has some subsequence that converges. And that's all there is. Okay? It would take me perhaps 1 or 2 lectures to recall the definitions of the weak star topology and to prove compactness. It's a basic thing. This is by compactness of the space of probability measures. Any such limit eta is, so what I'm saying is that this converges to some eta. Any such limit eta is a G invariant probability. It's also explained in the book, and it's essentially automatic from the form. It is to get C that we choose eta n of this form as an average of the iterates. Any accumulation point of this sequence is automatically, essentially automatically invariant. Well, this measure is our eta s. So the last thing that I need, so you see how I constructed, I want a measure, an invariant measure, such that when I integrate phi with respect to this invariant measure, I get the integral of s. So how do I construct this? How do I get eta s? First thing is this measurability argument to find this invariant section. Then basically I put a Dirac mass on each one of these vectors multiplied by mu here. That's what Cn means. This is essentially mu multiplied by a Dirac mass on each one of these points. And that gives me a measure in the product space. Now I need it to be invariant, but it is already located in the right place because this measure only gives weight. This measure only cares for these points, and these points by construction are points where we have the maximum growth. Okay? But it's not invariant, so I have to do something to make it invariant, and this is the usual trick. Take the Cesaro average, go to the limit, take the limit, and from the construction you also get that the integral of phi d eta s is equal to the integral of s d mu. I'm going to, maybe let me prove this. So integral of phi d eta s. So why is this true? Well, this is the limit when k goes to infinity of the integral of phi d eta s d eta nk, right? Because nk converges to eta s, Weak-Star topology. Now this is the same as the limit as k goes to infinity of, I'm going to use the formula for eta n, this formula here. Using this formula, this expression becomes 1 over nk, sum for j from 0 to nk minus 1, phi g j x nu n of x d mu of x. Just using the meaning, substituting this the formula for eta n. And this, what is this here? So what is this here? What does it mean to say that x nu n of x is in gamma? By definition, unfortunately I already erased. By definition, this is the same as saying that the sum j from 0 to n minus 1 of phi g j x nu n of x is equal to s n of x. This was the definition of gamma n. So this is 1 over nk s nk of x. This is nk. Right? This sum, this complicated sum for the points I'm interested in is equal to the supremum, and the supremum we call Sn of x. By the definition of gamma n. Good. Now, then what? Then we know that SNK, 1 over NK, SNK converges to S. By the sub-additive, that's what we proved first, that this limit exists because the sequence is sub-additive, and so and it is also part of the sub-additive ergodic theorem that the integrals also converge. Okay, so by the sub-additive ergodic theorem, this limit is the integral of S d mu. By sub-additive ergodic theorem. So it's not very easy to summarize the proof because the proof is relatively long and it uses more than one ingredient. First ingredient, measurability of this set to obtain this invariant section, to obtain this kind of measurable vector field with the property that the image is contained in the maximal expanding set. And from then, a standard trick in ergodic theory to construct an invariant measure. You take, you start with an initial measure, you take the average of the first n iterates, go to the limit. Well, the limit may not exist, but there always exists a some converging subsequence, and then just a straightforward calculation shows that any accumulation point satisfies the equality that we wanted, because we started by putting Cn in the right place, by putting it on top of points that realize the maximum. Okay, so that 3 or 4 ingredients. One thing that I didn't say, since this is true for every mu, then it goes to the limit. It goes to the accumulation point, and that's the other property here. Okay? So this proves the supremum part of the proposition, and the infimum part is exactly the same, just with the other sequence. And using super-additivity instead of sub-additivity. Okay. So it is time to become less abstract and go back to our linear setting. And so let's do that. So now we go back. So we have a linear cocycle as we have been considering, and the consequence that we are going to get from this proposition is the following. Let x goes to v of x be a measurable invariant subbundle So what does this mean? A function that assigns to every point in M some subspace. This is, so Vx Vx is a subspace of Rd. That's what what means subbundle. Vx is a subspace of Rd. Measurability we already defined. It means that you can find bases for these Vx that are given by measurable vector fields. And invariant means that Ax of Vx is equal to V of f of x. Okay. And then the statement is then for mu almost every x, these two limits these two limits exist. Limit 1 over n log an of x v. No, sorry. That's not what I want to say. An restricted to Vx is equal to the maximum of lambda x v, v in Vx. And the limit of 1 over n logarithm of a n x Vx inverse, so the conorm is the minimum of lambda x v. Okay. So what does this proposition say? It says that you take any invariant subbundle. So I have this Vx, and you you start iterating. So you iterate only restricted to this subbundle, and look at the two sides of this equality. This side measures the norm of the matrix. Okay, the norm of the matrix restricted to Vx. This on this side, I have the logarithm here. I have the logarithm of the maximum of Ax v divided by v, where the maximum is taken over all vectors in Vx. That's what is written here. Okay? And then I take the limit 1 over n goes to infinity. Okay, this norm here is the operator norm and means this. N. Okay? What do we have here? Well, we have essentially the same thing, but the difference is important. We have the maximum over v of the limit, well, actually only lim sup over n, 1 over n log an of x v. So what is the difference between the two sides? There's a little difference here. There's a divide by v, but this is completely irrelevant. I can put this v here. It doesn't change anything because then it's divided by n. This term disappears. The important difference is something that we rarely can do, which is to switch the positions of the maximum and the limit. This is the limit of the maximum, that is the maximum of the limit. Well, there's also the problem of this lim sup, which is not so important because we know we are trying to prove that the lim sup is a limit. But the important point is this switch of the two. Okay, so this is saying that the norm grows at the speed at which the strongest vector grows. The growth of the norm is equal to the largest vector growth. The growth of the norm is equal to the largest growth of individual vectors. Okay? And that's what this proposition is saying. So, this is also the reason, by the way, this is the reason why the largest exponent, lambda 1, which is just defined as the maximum over v of all Lyapunov exponents, coincides with this. This is defined as the growth of the norm. Okay, this is the where it is at this point that we get that property. Okay, the proof is in some sense you already know what the proof is, but unfortunately we have to work. We have to write things. So let me write them, but I'm not going to say much that is new. So first of all, we are going to use this proposition with these characters, with these choices. And then, so in this case, for P equals the projective space, Gx equals A of x, and phi x v equals log of A of x divided by v. For this choice, I already did this last time, so I can go a little bit faster. I think we have that. It's just replacing that the I of n, or say S of n, this is the sup over some well, this is just the logarithm of the norm of an of x. Okay. When you choose this, and then S of x is the limit 1 over n. S n of x is just lambda plus of x. And in just the same way, in of x is the log of the conorm and I of x is lambda minus of x. Okay, just translating this notation, the notation in that proposition, to our setting. So let me call this proposition 2 and this proposition 1. I'm sorry, I switched the order. There's something that I should have said before. There's something before I start proving this. There's a corollary of proposition 1 that I need. There's a corollary of proposition 1 that I need. The corollary says, for mu almost every x, there exists two elements, vs of x in P and vi of x in P, such that the limit 1 over n sum j equals 0 to n minus 1 phi g j x vs of x is s of x, and the limit now the corollary is a statement of this type here. Okay, that's why it allows us to prove this. But so let me first explain what is the difference between the corollary and what is written here. Here is written the following thing. For each n, you take the sup on v, and then you go to the limit as n goes to infinity. So, of course, by compactness and so on, each time the sup is attained, there is some v that realizes the supremum, but that depends on n. And then you take that supremum and you go to the limits. The corollary says that you can do better. You can choose your vector, vs. You can calculate this expression for this vector for every n, and then when you go to the limit, that gives you the supremum. Okay? Getting a vector v here that gives the maximum value, the supremum, for each n, depending on n, is easy. What the corollary is saying is that you can take the same vector, do the calculation for this vector, and you'll get the supremum. And the vector does not depend on n. Okay? That's the difference with respect to what is here. To the definition. This is just a definition. So how do we get that vector? I have to explain that first, and then I'll be able to prove proposition 2. So I'm going to prove one of them. I'm going to prove this one, the first one. So let's see if everyone agrees with this. I of x is less or equal than the lim inf 1 over n sum j from 0 to n minus 1 phi gj of x v. This is less than lim sup and this is less than Sx. for every v. For every v. Okay? Now this should be easy to see. For example, what do you do to calculate I of x? You calculate this expression for every v. Then you take the infimum. Then you go to the limit, and that's I of x. If you don't take the infimum, then your expression is largest, is larger. So when you go to the limit, you get a larger number. Okay? Except that in that case, you don't know whether the limit exists. That's why I wrote lim inf. Okay? If you remove this infimum, your number grows. If you remove this supremum, your number decreases. That's all I'm saying there. That's true for every v. Now, on the other hand, by the ergodic theorem, that's where the miracle is going to happen. By the ergodic theorem, I said you don't know that the limit exists, you don't know whether the limit exists, but in fact you do. By the ergodic theorem, the limit exists for almost every xi v, eta almost every xi v, given any g invariant probability. Okay? This is precisely the discussion that I had last time at the end of the class on Tuesday. We want to prove in the Auxiliaries theorem that the limit exists. First, we have to work with lim inf and lim sup. But the miracle is that if you have an invariant measure, then almost everywhere with respect to that invariant measure, the limit exists. Okay? So, and we do have an invariant measure. We actually have two invariant measures, eta s and eta I. So if you take eta equals eta s, you conclude that for eta s almost every pair xv, this limit exists. Let me give it a name. Let's call it phi twiddle xv. By definition, is the limit. So phi twiddle exists. And that's phi twiddle exists. And the ergodic theorem also says that the limit is equal, the integral is equal to the integral of phi itself. Okay? Now, by the first proposition, the proposition 1, this is equal to the integral of S d mu. So we have the following situation. This lim sup is a limit almost everywhere. what is written here is phi twiddle. It's a limit almost everywhere. It's always smaller than s of x. Okay. It's always smaller than s of x. And the integral is the same. So if I combine this with the fact that phi twiddle is less or equal than s, I conclude that they have to be equal for eta s almost every pair. Okay? Well, if I were in your place, I would feel a little bit uncomfortable because I'm comparing two types of functions. I'm comparing a function that depends on x and v with a function that depends on x only. So this inequality doesn't make much sense. I mean, I'm going to make it sense, but it doesn't make much sense because the domains are different. However, that is not so important. What I mean here is that psi twiddle of x v is less or equal than s of x. And then, of course, I can think of this as a function that depends on v but does not depend on v. A function in two variables that does not depend on the second one. Okay? So that's what I mean, and that's what's written here. Okay? Okay, so what I have achieved so far is that the kind of equality that I want, look at what is written here. What is written here is that phi twiddle of x vs of x is equal to s of x. It's precisely that. That's precisely what I want. This left-hand side is phi twiddle, and this is s. So this equality that I want is precisely of that form. So what I know is that this equality is true for almost all pairs. And I want to prove that for each point x, I can find a vector v where the equality is true. So exercise if a set E has full eta s measure, which is precisely what I proved here, the set of points where this equality holds as full measure, then for every x, for mu almost every x in M, there exists some vs of x in P such that x vs of x belongs to E. So we have a product. What I've just wrote has the following meaning. We have a product, M, P. We have a measure eta s that projects down to mu. It's part of here. And then I'm saying that if you have a set here, E, with full measure, then for almost every x, there is some point v s of x that is in the set E. A set that has full measure has to intersect almost every vertical. It's a simple exercise. So that's the end of the proof of the corollary. Well, as I told you last time, we prove 95% of the theorem in 5% of the time, and then we prove the other 5% in 90% of the time and energy and effort. This argument is not at all trivial, and it's not elementary. The idea, the strategy behind is to try to use the ergodic theorem to turn limits into lim sup, to prove that limits actually exist, and that's what we are doing. I'm not trying to do all the calculations, because otherwise you will get too bored, and besides it's much more efficient to do these calculations alone. But this is the strategy. Okay, so at this point I proved the corollary that I had forgotten, and now let me go back to proving this proposition. I was here. Okay, so let's continue. With the proof of proposition 2. Okay. So, I mean, now it's very easy. By the corollary, there exists some vector vs of x for mu almost every x. There exists some vs of x where we have this equality. But what does this equality mean? It means that the lim, I mean, just doing the translation, of 1 over n log of anx restricted to vx, that's the is equal to this side here, and this side is is lambda x vs of x. Okay, this here corresponds to this, with the advantage that we even know that the limit exists. and this corresponds to this. Okay. Fit wheel and S. So I think the proof is completed because this inequality. So what this proves, this shows okay, let me see. Let me ask a question. When I'm trying to prove this, as I explained, I'm trying to change the two. Now, one inequality is obvious. Which one? Which one? This one? This one is obvious. Let's see why. If I hide this, then it's obvious, isn't it? Here you take the maximum, and then you go to the limit. Here you go to the limit without taking the maximum. So this number is bigger than that one for any v. Right? If it is bigger for any v, it is bigger than the maximum. Okay? So, this inequality is obvious. So what we had to do to get proposition 2 was the other one. How do you prove the other one? You take this expression, it is here, and you find some vector whose lambda is bigger than this one. Okay? You take this expression here, that's what is written in blue there, surrounded in blue. You take this expression and you find some vector such that this expression is bigger than this one. I found that vector, so I proved this inequality. Oof. Okay. So we have proposition 2. Corollary for mu almost every x, lambda 1 of x is lambda plus, and lambda k of x is lambda minus. Okay. Well, it's you just the proof. You just take Vx to be everything. Take Vx equals Rd. Then this side here is lambda plus. Okay. This is lambda plus. And this is the largest of the lambdas that I call lambda 1 by definition. So I don't have to do anything. Okay. This corresponds to lambda plus, and this corresponds to lambda 1. The only thing is that in this proposition I wrote a more specialized version, where I have this restricted to any measurable invariant subbundle. Okay, we are getting into the final step of the proof of the Arcelidus theorem. And now it will be I call it dimension reduction. Well, it's not really the final step yet. So we're going to consider the following situation. So we are going to let x goes to Vx be a measurable invariant subbundle. Essentially the same situation as in here. And I'm going to consider two functions, alpha and beta. Measurable functions. When I say function, I usually mean real function. With alpha strictly smaller than beta, and two other properties. Lambda xv is less or equal than alpha if v is in Vx, non-zero. And lambda xv is bigger than beta if v is not in Vx. Okay. So the situation that we want to consider now is that we have some invariant subbundle Vx. And we have two different types of behavior. If a vector is contained in Vx, then it grows very slowly. It grows not faster than alpha. So any vector that is in Vx grows at a rate that is bounded above by some small function. If the vector is outside Vx, then it grows faster. It grows rapidly. The rate of growth is bigger than beta, and beta is bigger than alpha. Okay? So V is a subspace where vectors grow slowly, and outside this subspace, vectors grow very rapidly. So here's what I'm going to state now in this situation. We're going to write the matrix A as in this form. B of x, 0, C of x, D of x. I'm going to explain this. So I have the V of x. By invariance, it goes to V at f of x. Okay. And I call B of x is the restriction of A of x to Vx. This is a map from Vx to Vf of x. That's what B means. Okay? By definition of invariant, this subspace is mapped to this subspace. Then what this expression here means is the following. I consider here the orthogonal. And here the orthogonal. So I have a direct sum Vx, orthogonal. Here I also have a direct sum analogous. And my map A is a linear map from this direct sum to this direct sum. So this is the representation of this linear map with respect to these sums. Okay? So B goes from Vx to Vf of x. C goes from Vx I'm sorry, this is D. And this, I want to write the sum differently. This first the orthogonal and then the space. Otherwise, I would have to. I prefer to write it this way. So D goes from Vx to Vf of x. C from Vx orthogonal to Vx. And B from Vx orthogonal to Vf of x orthogonal. Okay? Just let's see if we are clear with this notation. Why do we have a 0 here? The reason is, and not here. The reason is that if I take a vector in Vx, a vector that only has orange components, and I look at the image is also in Vx. Okay? That's the fact that the subspace is invariant. If a vector is inside here, then the image is inside there. However, we do not assume, we do not know, it's not true in general, whether the orthogonal is invariant. So if we choose a vector v in the direction of the orthogonal, the image usually is not in the orthogonal. And then C tells us what is the component in the direction of f of x, and B, what is the component in the direction of f of x orthogonal. Okay? So C is 0 precisely if the orthogonal is invariant. Okay? proposition says, proposition 3 says that for mu almost every x, for every u in the orthogonal, and every v in V, lim sup 1 over n log of b b n x u is equal to the lim sup 1 over n a n log a n x u plus v. And then this limit exists if and only if this one exists. And then they are equal. Okay, what is the proof of this proposition is a calculation in linear algebra. It's much more important to understand why we like this proposition, why it is useful. So first, what is important is to understand what it is saying. We have Vx, and remember, vectors in Vx grow slowly. Vectors outside grow fast. So let us take, and we have the orthogonal, right? And we have the orthogonal. Let us take any vector, any vector. This vector can be decomposed with a component along the orthogonal that I'm going to call u, and then a component along Vx that I'm going to call v. Okay, so this is the meaning of those two objects in the statement. U is a vector along the orthogonal, v is a vector along the Vx, and we are looking really at the sum, u plus v. Okay? So what does the first part of the proposition say? It says that if you want to understand how the sum grows, you don't need to look at v. You just look at the orthogonal direction. Let's see, do we believe in that or what? Let's think a little bit. This vector is growing slowly. The other one grows fast. If I look at the sum of the two, the fast one is going to determine how the sum grows. So yes, we believe in that. Okay, it is saying that if you are adding a vector that grows slowly and one that grows fast, the sum will grow as the fastest grows. And that's what's written here. Well, not quite. It's better than that. Because when I use the word grows, I was thinking of two different dynamics. This statement says that u plus v grows under iteration by a at the same speed as u grows under iteration by b. So what is b exactly? How do we define b? What does b of x do? B of x takes the vector u, you calculate the image. Okay, you take this vector u, you calculate the image, but you see the image is not necessarily in Vf of x orthogonal. Okay, the image of my vector u usually is outside orthogonal, because the orthogonal is not invariant. But then you project this to the orthogonal, and that's what b means. So first you iterate by a, then project to Vf of x orthogonal. Okay, B is a linear map. B of x is a linear map from the orthogonal to the orthogonal. What is the definition? First you apply A, and then you project to the orthogonal. Okay, and the lemma. So this is a new cocycle defined on the orthogonal, and the proposition is saying that your growth in the ambient space does not depend on the component of V, which is, I think, acceptable because we already know that these are the guys that grow slowly. Not only it does not depend, but it is equal to the growth along the orthogonal for this new cocycle. Now this is fantastic, and the lim sup is a limit here if and only if it is a lim sup here, and then the two limits are the same. Why is this fantastic? Because it transforms the problem in the ambient space Vd into a problem restricted to the orthogonal. And the orthogonal has dimension smaller than the ambient. So this will allow us to finish the proof of the Oscillides theorem by induction on the dimension. If you know that the theorem is true for Vx, then with this proposition, you move the conclusion to higher dimension. Okay? That's why this is important in the proof. I'm not going to, I think we already had epsilons and deltas enough for today. I'm not going to prove this right now. You're probably tired. But this is how we are going to use this on Tuesday. I won't be here on Monday. So next class will be on Tuesday. Okay, and that's enough for today.